Section 7.7 is on page 554, talks about approximate intervals or integration. We did something with this back in the days in first semester calculus when we did the left-hand approximation, right-hand approximation, and midpoint approximation. And the reason we're learning this after learning techniques of integration, because some intervals are not possible or impossible to integrate using the techniques that we learned so far. Some of those are the integral of e to the x squared dx, the integral of e to the x over x, the integral of the sine of x squared dx, the integral of the cosine of e to the x, and there are plenty. Those are few. So, we really approximate using three rules. We have three rules to consider. One we already know. That's the midpoint rule. And here they are. What do you want? So the midpoint rule. If I want to integrate the integral from a to b of f of x dx, the midpoint using n subintervals, delta x is b minus a over n, the usual. And if we remember, x sub 1 was the midpoint, x sub 2 was the midpoint. So if you take x sub I minus 1 to x sub I, the midpoint of that, and the endpoints, and divide them by 2, and there it is. They're introducing this trapezoid rule. We talked about that a bit back in the days. So instead of using a right hand or a left hand, what they do, they say, hey, why don't you go straight? Oh, okay, let's do it again. Instead of doing a left or a right, if you take each of those, instead of doing a left or a right, they run a trapezoid every time. So we're not deriving those. And trapezoid rule works. I used to derive this, but we just need to use it a bit. We're more interested in the error than anything. Delta x is identical to the previous delta x, b minus a over n, and x sub I is matching what Riemann did. You'll notice the only exception is you start with f of x sub 0, and you end with f of x sub n. The left-hand approximation, we picked x sub 0 and we dropped x sub n. The right-hand approximation, we dropped x sub 0 and we picked x sub n. Here we're adding both. So whatever n is, a note is, if this is t sub n, there's going to be one more evaluation than the number of intervals. So if you find t sub 5, there's going to be 6 of those. And we notice that everything in between picks a 2. The Simpsons rule, well, it's slightly different. Delta x is the same. And you start with delta x divided by 3, and the same idea applies. This is still n plus 1 calculations. But with the Simpson, we notice that the first and the last are there, which means we have one more. And we notice the second and the second to last are a 4. The third and the third to last is a 2. So we start with the outside-most two intervals. The outside-most calculations pick nothing, then a 4, then a 2, then a 4, then a 2, which indicate that n must be even whenever I'm using the Simpsons rule. So it's not that bad if you have those, if you get those out of the way. It's really simple to use, and I just want to do one example on those, and then we have this error bound we're going to get into, and we're going to tackle the error bound heavily in chapter 11, which We're almost there. So I want to pick a problem from the book. I'd like to look at page 564. And I want to tackle one of those. Directions here. Use the Trapezoid Rule, the Midpoint Rule, and the Simpsons Rule to round to 3 decimals. Some of those you can integrate, many of those you can't. It doesn't matter whether you can or can't, it makes no difference. I'm going to pick something that, okay, let's pick number 16. So on your test, I could pick any of these problems, but I'll choose n to be small, 4 or 5 at most. So I have this interval, and I'm looking at running from 1 to 3, and I'm cutting this into 4 subintervals. So delta x is b minus a over n. That is 2 over 4. That is 1/2. So this is 1, this is 1.5, this is 2, this is 2.5, and this is 3. And pretty much I need that for all of those. This is where I begin, and this is where I terminate. And n is 4 of those. If I want to use the midpoint rule, so if I want to go by m sub 4, well, that is the integral from 1 to 3 of the sine of t over t dt. If I want to use the midpoint rule on this, I will say that's delta x times f of the midpoint of those, 1 plus 3/2, that's 5/2. Take half of that, that's 5/4. 3/2 plus 2 is for 7/2 multiplied by a half, so 5/4, 7/4, 9/4, and 11/4. Pretty much those are the values I need. And I'm going to plug this in my calculator, and I'll tell you what that equals in a minute. I'll calculate all of those at the end. If I want to find trapezoid t sub 4, well, that's the integral from 1 to 3 of the sine of t over t dt. That's going to be delta x divided by 2 in this case, times f of 1 plus, I'm going to leave some space, f of 3/2. So here we're just taking this, 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 and this. Plus leave some space, f of 2, leave some space, f of 3/2, leave some space, f of 3. So you notice here we have 1, 2, 3, 4, 5, even though we're finding 4 subintervals. And I'm going to copy this down. What happens, this takes a 2, this takes a 2, and this takes a 2. I'll plug this in the calculator and figure this out in a minute. And I'm going to take s sub 4 for the integral from 1 to 3 of the sine of t over t dt. That's going to be delta x over 3 times, oops, I messed up. I did copy this, right? Okay, this is acting up. There it is. Awesome. So if I want to take s sub 4, well, all what I have to do is alter that and make that a 3. And guess what? All what I need to do is make this and that a 4, and the inners a 2. And there it is. and I plug that in my calculator, so I could go back on my calculator and just replace those two, and that's it if it's only 3 of them. Now, if I plug this in my calculator, this is what I'm going to get. And these are the 3 values I got from my calculator, and you notice those are accurate. If you round, it turns out I copied the wrong number from my calculator, I'm sorry. So when I look at those, they're accurate to, oh boy. One more time. I'm sorry guys, it just takes a lot of time to redo this, so I copied that. Okay, these are the numbers. That's what I actually got from my calculator. I just mixed up the numbers, I'm sorry. So, you notice they're accurate to 2 decimal places. Not a big deal. This is really a straightforward portion of the section. The part you really want to pay attention to is the error bound. And the error bound looks slightly different. It's not a lot of work. It's not that tough. Let me go down. Oh, here it is. Awesome. Oh, come on. So, there's an error associated with each of those. And let me just elaborate on that really quick. And the error here is error in using trapezoid. B we know, A we know, N we know. Error in using midpoint. B we know, A we know, and N we know. And in using Simpson, B, A, and N we know. You'll notice the only thing that's going to vary is this K. That's all you really have to worry about. Now the K for using the midpoint and the trapezoid, K is the biggest the second derivative could ever be. So it's the maximum of f double prime. And Simpson is a bit tougher. It is the maximum the fourth derivative could ever be. Now this is going to be a bit tricky. That is, if I call this g, and I told you I want to find the maximum of this function g. How do you find the maximum in calculus? Don't you take a derivative, set it equal to 0, and see where is it not defined? And if g equals f double prime, doesn't that mean I'm really gonna be finding the third derivative in both of these cases? And if I call this g, and I said, how do you find the maximum of a function g? Don't you take a derivative, see where does it equal 0, g prime not exist, right, from calculus? Well, if g is the fourth derivative, and I take a derivative of that, isn't that the fifth derivative? Now you have an option. That is, if I am certain that this function is decreasing, then I know the maximum is the left endpoint. And if I know a function is increasing, then I know the maximum between A and B would be the right endpoint. So if I'm certain that this function is increasing or decreasing, I could save myself a derivative. But if I don't, then guess what? I will have to take the third derivative set equal to 0, or the fifth derivative I'm using Simpson. So in the next example, in the next video, I'm going to do 2 examples on those and get those out of the way.